It is really my pleasure to be here, and thank you so much for Michel for organizing this beautiful series of lectures and for the invitation to speak and to address the Collège de France. So the work I'll tell you about today is work that we're doing in my lab where we're building small, that is micron scale, mechanical oscillators that interact, exchange energy with superconducting electrical circuits. I show you an image of the kind of devices that we'll be working with in this first slide, where I show the little mechanical element up here and then the rest of the superconducting circuit down here. The people who have worked on this project with me include various postdocs and graduate students. The work I'll show today is primarily that of my postdoc Tano Palamaki, former postdocs John Tufel and Cindy Regal, and graduate students Jen Harlow and Reed Andrews. I'd like to begin my presentation by looking back in time to an era when mechanical oscillators, in particular meter-scale mechanical oscillators, were the precision measurement tools of that era. The way in which 300 years ago or 400 years ago one measured time as accurately and precisely as possible was using these meter-scale pendulum clocks, or the way one measured the most feeble forces, the most weak interactions that were known at the time using things like Cavendish balance. But if we look in our laboratory, our modern physics and physical sciences laboratory today, these sort of meter-scale mechanical oscillators play a relatively small role in most cases. Certainly the precision measurement tools these days are based on optics or on electronics. That is to say that the quantity of interest with which we would like to measure, we arrange for some way for that quantity of interest to modulate a laser light field or an electrical signal. And then we use the tools that produce those light fields and measure them with very high dynamic range. That is to say, lots of ability to measure large signals with very little fluctuation, very little noise, to make a precise measurement of the quantity of interest. And when that paradigm works well, when we can naturally map something that we'd like to measure onto a light field or onto electrical signal, this procedure becomes something we almost forget about. It's so transparent. There are particular situations where the thing we'd like to measure, the thing we'd like to learn about, does not naturally interact with a light field or an electrical signal. To cite a couple of prominent examples from the literature, if we'd really like to measure the density of nuclear magnetic moments inside of a small biological molecule, or we'd like to know the low-lying electronic states in a small and completely isolated metal ring, those are physical quantities which we cannot measure just by shining light on a virus particle or attaching wires to it. We'll not access the degrees of freedom we desire. In situations like that, a kind of measurement strategy, almost of last resort, is to arrange for the system of interest to interact with our optical or electrical probe field by imposition of some kind of mechanically compliant structure, a mechanical oscillator. Schematically, we can imagine that we just arrange for the system that we'd like to study to exert some kind of force on a mechanical structure, and the resulting deflection we read out with our optical or electrical field. And of course, this is the strategy that's used in a commercial product known as an atomic force microscope, but it exists in many other contexts. In some sense, one can even imagine the gravitational wave interferometer, like LIGO, falls into this model. The torsional oscillators used to measure the phase diagram of liquid helium, in certain sense, meets this kind of measurement strategy. And I would summarize very broadly the strategy, the thing that we are pursuing in my laboratory and is being pursued in many other laboratories, is the idea that we should take this notion of using a mechanical oscillator to create a synthetic interaction between two systems that don't otherwise exchange energy naturally, and to bring that strategy into a regime of quantum behavior, where very literally what we would like to do is map the quantum state of a system of interest deterministically and reversibly onto the state of a mechanical oscillator, and then to deterministically and reversibly map the state of the mechanical oscillator onto a light field or an electrical signal, for which we have the ability to prepare systems in pure quantum states, and for which we can make measurements that are limited only by quantum projection noise. Now, that notion, that strategy, is immediately confronted by the following unfortunate experimental fact. Mechanical oscillators are generally classical objects. By that I mean the following. Any mechanically oscillatory structure which is going to be sufficiently compliant, soft, that it can respond to feeble forces, will have a resonance frequency which is sufficiently low that the inevitable coupling of this mechanical oscillator to some kind of thermal environment, that environment will inevitably be hot enough to ensure that there are lots of thermal excitations in that mechanical oscillator. Even if the environment is cooled far below ambient temperature, there'll still be many thermal excitations left behind in this mechanical oscillator. We can refer to that as sort of the number of phonons per mode in the environment, and that will be a number much bigger than 1, typically. And that will spoil, if we don't do anything about it, this notion of creating a kind of conduit for quantum information, a sort of quantum bus that uses the mechanical oscillator as that conduit, as that bus. Fortunately, we can overcome the classical nature of the mechanical oscillator. It can sort of inherit a pure quantum state via an interaction with this probe field. If you can make the probe field, the thing that we can prepare in a pure quantum state, if we can make the interaction between that and the mechanical oscillator much larger than the coupling between the mechanical oscillator and its thermal environment, then the mechanical oscillator can be prepared in a pure quantum state. And that's sort of part of the problem, part of the challenge of bringing these mechanical oscillators into a regime of quantum behavior. There's, of course, related requirements. We need to be able to make measurements of this probe field and then infer the state of the mechanical oscillator in such a way that the noise associated with the measurement of this probe field leads to an apparent motion, a sort of fictitious motion of the mechanical oscillator, which is small or at least comparable to the zero-point motion of that object. And we'd like to be able not just to prepare the mechanical oscillator in its, say, in its ground state, in a particular pure quantum state, but to be able to then manipulate it to prepare it in several different pure quantum states. And that can be done by turning these, this interaction and this interaction on and off in a fast way. And I'll show you some progress on all of those different requirements, things like state initialization, state measurement, and state manipulation in this talk. And I think I have to confess, and I do in a sense mean confess, a second reason why I find the notion of bringing a mechanical oscillator into the quantum regime as an appealing or desirable problem to work on. And it's nothing so practical as the notion of using it as a kind of tool of quantum information. It's really based on the fact that at some point we are all introduced to the theory of quantum mechanics, and its strange aspects are quite arresting. And yet, after some time, we become rather accustomed to the idea that, well, the behavior of small things like electrons, molecules, photons, ephemeral and ethereal things, we imagine are sort of naturally described by quantum mechanics. But still, if we believe this is the correct theory of nature, it should, in principle, apply to big things, big, tangible, and mundane things. And so we ask ourselves, sort of, what's the biggest, most ordinary-looking thing that we can make that still behaves quantum mechanically? And that's not something for which I have a simple scientific story as to why we will find some deviation or modification from orthodox quantum theory, but simply a kind of inspiration that it would be very strange to see some mechanical oscillator really be in two places at the same time, particularly when that mechanical oscillator would be a big object, something of the scale I'll show you today that you can see with your naked eye without benefit of any kind of microscopy. In fact, it's comparable in size to a unit of the currency of the United States. It's also about the same size of one of those euro cents. And these objects are not only big, but they're tangible. You hold it in your hand and you can see the quantum superposition is between some little hunk of material in one place and in another place at the same time. And that is certainly an inspiration to me and to the people in this field. Okay. And there's a large community of people who work essentially on this problem, a large and growing community of people, and a substantial fraction of them pursue the idea of preparing, controlling, and measuring the motion of a mechanical oscillator by interacting with it using a laser light field, specifically a light field that is confined into a Fabry-Perot cavity. So the essential notion is simply to support one mirror of the Fabry-Perot cavity on a light mass and a compliant spring, and to have a second mirror which is fixed in space, confining light between the two mirrors. And then there's an interaction between the position of the mechanical oscillator and the intensity of the light field stored in that cavity. And that interaction, as we heard in the first talk today, is something which will allow us to manipulate and to measure the motion of the mechanical oscillator. I can show an image of such an experiment. Comes from Marcus Aspelmeyer's group in Vienna, where this is a scanning electron microscope picture of a little mirror that is supported on a doubly clamped cantilever of silicon nitride. If you were to push down on that mirror, not with your finger, but with a light field, it would deflect. And indeed, a second fixed mirror, which is not in this image, would give you a light field stored between the two, and the intensity of the light field will push on the mirror in such a way that by measuring the phase of the light field emerging from that cavity, we'll be able to infer the position of the mechanical oscillator, and we'll be able to push or exert a force on the mechanical oscillator. And in principle, that force can be dissipative and can cool the mechanical oscillator right down to its motional ground state. Okay, I'll show you sort of a series of pictures of different versions of this experiment. There are many that exist around the world, some of which look very much like literal Fabry-Perot cavities. Others have a more a kind of analogous interaction where it's hard to see where there's exactly a mirror. The kind of microphotonics work of Oscar Painters at Caltech sort of is more or less a kind of freely suspended photonic bandgap material. Later in this series of talks, we'll hear from Tobias Kippenberg about these toroidal cavities. But then there are these larger structures that really look like mirrors. This is a 1-gram mirror suspended from a couple of strings that you can't see in the picture, and a very kind of large and macroscopic Fabry-Perot cavity. In fact, there are not only many versions of this experiment around the world, there's several inside of the city of Paris itself. Okay, I understand it's a big city, but still, it's quite a large amount of activity in this area now. In my group, we eschew the choice of optical light as the way to interact with and to measure the motion of a mechanical oscillator. Instead, what we do is build an electrical circuit which is the strict analog, as we heard earlier, of a Fabry-Perot cavity with a movable mirror, but it's built from an inductor-capacitor resonant circuit where we've arranged the motion of a mechanical oscillator such that its motion will alter the separation between the two plates of a capacitor, altering the resonance frequency of that microwave resonance circuit. And then there'll just be a way in which we can inject and extract microwave energy from that circuit, and that realizes something which is described by the same Hamiltonian as the Fabry-Perot cavity with the movable mirror, at least in the approximation that Michel described. And what we find so appealing about working with microwave light rather than optical light, it has a kind of technical nature. It is possible now for us to cool the environment in which this circuit lives inside of an ultra-low temperature cryostat to temperatures of about 20 milledegrees above absolute zero. Nothing about microwave electronics, microwave electricity using superconducting circuits is incompatible with operation at those ultra-low temperatures. It's very natural to work at microwave frequencies at these low temperatures. And while that temperature is not cold enough, say for a 10 megahertz mechanical oscillator, to ensure that the environment is cold enough to prepare the mechanical oscillator in its ground state, you are 4 orders of magnitude closer than you would have been at ambient temperature. That's a big help. Okay. And so our goal is to create an interaction between electricity and the microwave fields running through a nearby transmission line, which will be big compared to this decoherence rate of the mechanical oscillator due to its coupling to the thermal environment. And we win a big factor just because the environment is now much colder than it would be at ambient temperature. Now, in starting this work, I was really inspired by 2 previous versions of experiments of this type. And I'm also amused by the fact that they're maybe most closely associated with the city of Moscow. The first sort of version that I think about is experiments that took place in the 80s with the intent of detecting gravitational waves based on building microwave cavities, which had a style such that a passing gravitational wave would strain the cavity in such a way that the resonance frequency of the cavity would be altered. And this is the work that was started in Moscow State University by Vladimir Brzezinski and his coworkers. And what we're going to build is a kind of lumped element, smaller version of an experiment of this type. But there was an even earlier version of this sort of structure, a microwave resonance circuit whose resonance frequency would be modulated by some kind of strain field. And that has maybe a less scientific basis. It's more involved with spycraft. In the 1950s, when the United States built its new embassy in the city of Moscow, the ambassador was given a gift from the children of the Soviet Union, which is this beautiful, meter-sized, hand-carved wooden plaque where the carving is the Great Seal of the United States, containing all of the symbology of the American state, the proud eagle clutching in its talons the arrows of war and the olive branch of peace. And up here is this disk, including the 13 stars of the 13 original colonies of the United States. Hidden behind this object, carved in a cavity, was a thin membrane coupled to a capacitor and then an inductor, which took the form of a meter scale antenna. And a fellow sat across the street from the US Embassy with a 300 megahertz transmitter, illuminating this structure. And of course, the 300 megahertz radiation was scattered back, but not until it was modulated by the voices of the people in the room. It's a beautiful and incredibly clever piece of electronic surveillance. In particular, it's completely passive. There are no batteries attached to that thing. I know that, for example, it took several years for the United States to discover the existence of this bug. They were sure that they were being bugged, but they didn't know how. And then once they discovered it, it took them several more years to figure out how it worked. And I promise it won't be so complicated these days. We're rather accustomed to experiments of this type. Here is our version of that little Soviet listening device. The structures we build are spiral inductors, here shown in the main figure as a cartoon, with a pair of metal plates in parallel forming a capacitor. And then there's a transmission line that slides nearby and can inject and remove microwave energy from that inductor capacitor resonant circuit. The microwave circuit resonates at about 7.5 gigahertz, but that's modulated by the separation between the two plates of this capacitor. The bottom plate, the capacitor shown here in the scanning electron microscope image, the bottom plate is sitting on an insulating substrate, but the upper plate is freely suspended. It's held around its edges, but it's free in the middle and can move up and down, and does so at about 10.5 megahertz. And in doing so, it modulates this 7.5 gigahertz resonance frequency. So we can then make a kind of electrical model for that circuit, just an inductor capacitor resonance circuit where the capacitance is modulated by the motion of a mechanical oscillator, and write down a Hamiltonian for that. And it's a Hamiltonian we've already seen today. We can just count the energy stored in the resonant circuit, in the motion of the mechanical oscillator, and the interaction between the two. And the interaction between the two is just counting the number of photons times the deflection of the mechanical oscillator. One important scale in this problem is how much does the frequency of this circuit shift per unit 0-point motion, per 0-point motion of the mechanical oscillator. And that's a quantity I'll call capital G. It's the same thing that Michel called G3. Well, he said that in French. I can't do that. So. You can compare that rate to other dissipative rates in the problem. And in particular, one important dissipative rate will be the rate at which microwave energy leaks in and out of the circuit into these propagating or itinerant microwave fields. Now, this interaction Hamiltonian by itself is relatively weak. This G up front, in our case, will only be a few hundred hertz, and the dissipative rates in the problem will be a little bit faster than that. But we can greatly enhance this interaction if we excite the circuit with a microwave tone. And if we excite it with a microwave tone detuned from the circuit's resonance frequency by the mechanical oscillator's resonance frequency, we can linearize this nonlinear interaction and arrive at a linearized interaction Hamiltonian, which is exactly the same Hamiltonian as a beam splitter, except that now it's a beam splitter not between two modes of electromagnetism, but one mode of electromagnetism denoted by the A's and a mode of mechanical motion. And I'll refer to those modes, the quanta of that mode, as being phonons. And so this interaction Hamiltonian annihilates photons at the circuit's resonance frequency and creates phonons, units of mechanical motion, quanta of mechanical motion, and vice versa. We also create microwave photons at the circuit's resonance frequency, which weren't there before, while annihilating quanta of mechanical motion. And the strength, the prefactor in front of this beam splitter Hamiltonian, is a quantity that's under my control. It's how strongly I drive detuned from the circuit's resonance frequency. And that leads to a kind of transfer rate, a rate of conversion between phonons and itinerant photons at this rate capital gamma. Okay, so the first thing we can do with that interaction is just use it to measure the motion of the mechanical oscillator. We'll take our circuit, place it into a kind of two-arm Mach-Zehnder interferometer. The upper arm in this interferometer, that'll just provide a phase reference. The lower arm will inject this detuned field. That will create an interaction between the mechanical oscillator and the resonant circuit. New microwave photons that weren't there before at the circuit's resonance frequency will leak out of the circuit. Those are sort of the annihilated phonons. And we then interfere that microwave field with a copy of the tone we injected in our Mach-Zehnder interferometer and mix it down to a convenient frequency. We can then look at the spectral content of that mixed down frequency, and when we do that, we see a sharp peak right at the resonance frequency of the mechanical oscillator. And that corresponds to the real thermomechanical motion of the oscillator. It's in equilibrium with an environment at about 20 millikelvin. It has a kind of Brownian motion associated with that, and we can resolve that tiny motion using these microwave measurement techniques. In particular, in this graph, I have calibrated the y-axis in units of femtometers squared per hertz. The electrical signal has been converted to an apparent motion of the mechanical oscillator, and you can see we can really measure with displacements on the order of a Fermi of 10 to the minus 15 meters. And from data of this type, we can determine the line width of the mechanical oscillator. That's how strongly coupled it is to the environment, as well as the properties of the resonant circuit and how quickly the resonant circuit decays to propagating or itinerant microwave fields. Okay. So indeed, we can really demonstrate to ourselves that we're looking at Brownian motion if we adjust the temperature of the environment and look at the area underneath a curve of this type. When we do that, the area underneath the curve plotted on the y-axis is just proportional to the temperature of our environment in the way that we expect from the equipartition theorem. And we've done something very provocative here, something we have chosen to plot the completely classical quantity, the area underneath this curve, in kind of quantum units. We've divided that average energy by the phonon energy and refer to that quantity as n, the number of phonons in the mechanical oscillator. And from the slope of this curve, we can extract the interaction rate inside of the Hamiltonian. And now we can begin to think about preparing the mechanical oscillator in its motional ground state. In particular, you might be concerned because in the act of measuring this mechanical oscillator, what we are doing is annihilating quanta of mechanical motion and to create the photons that we measure. But in this experiment, we always ensure that the rate at which that annihilation process happens is small compared to the rate at which the environment is usefully heating our mechanical oscillator back up. So we don't change the temperature very much. We don't have to do that. We can measure more strongly. And when we do that, these peaks that correspond to the thermomechanical motion, we resolve as we increase the strength of measurement. And in doing so, we are more rapidly scattering phonons, turning them into photons that we then measure. But that also cools and damps the mechanical oscillator. You can see that as the line width of the mechanical oscillator broadens, and the rate at which we are removing energy is just, you can just read off from the width of these Lorentzian peaks. And the area underneath the curves also goes down and down and down, indicating that we have less and less average energy in the mechanical oscillator. If you don't believe me that the area is going down, please notice the logarithmic scale on the y-axis. Okay. So we can, plot or name the average number of quanta in the mechanical oscillator, the area underneath these curves. It goes down to less than 1 for this yellow curve in the bottom. In fact, we can keep turning up the strength of that interaction and just plot the average occupancy of the mechanics as a function of the strength of measurement. At the same time, we plot the rate at which we extract energy as these red triangles. And indeed, when we cross a boundary here, this dimensionless number, which is just the rate at which we're extracting energy, divided by the kind of decoherence rate in the problem, this is the condition for cooling to the ground state. And we can go well past that point. And so we have a kind of many photon cooperativity parameter, which allows us to ensure that the mechanical oscillator, as far as it's concerned, it's more in equilibrium with the light field than it is with anything else. And if the light field is in a pure quantum state, so will the mechanical oscillator. Okay. And that's a kind of completely steady state and story, but we can turn on and off the interaction between the mechanical oscillator and the microwave fields quickly. And we can exploit that to do things like manipulation, to really imagine that the sorts of things we're doing in cooling and in measuring correspond to a kind of state transfer from mechanics to electricity and vice versa. And now we can do that state transfer in a temporal way. I'll show you that we can ask, in fact, a kind of maybe technically relevant question, at least in the context of quantum information. Could we use these mechanical oscillators to act as a kind of quantum memory for itinerant or propagating microwave fields? Could we take a microwave photon propagating in a transmission line, snatch that object, that excitation, out of the transmission line, stuff the information that it encodes into the motion of a mechanical oscillator, and have it live there for a period of time longer than it would have lived as a propagating microwave field, much longer than it would have lived as a propagating microwave field, and then at some later time go and recover that information, turn it back into a propagating microwave field, a sort of microwave photon catch and release. That notion, again, is confronted by the coupling of the mechanical oscillator to the environment. We need to be able to have this rate, the interconversion of propagating microwave photons to mechanical motion, far exceed this environmental decoherence rate. But as we've seen, that's the condition that says I can make the cooperativity larger than 1, and we're comfortably in that limit. So now we can begin to pursue notions of this type. So once again, we can turn on our detuned microwave field, create an interaction between the mechanical oscillator and the resonance circuit, and that creates new microwave fields that leak out at the circuit's resonance frequency. The only distinction is that we're going to be able to turn on that interaction and turn it off in a fast way. So there are going to be sort of two separate regions of frequency with which we excite this microwave circuit. Far detuned from the circuit's resonance frequency, microwave fields injected at that frequency serve only to turn on and off the interaction between the mechanical oscillator and the circuit. They kind of they create and remove the interaction. On the other hand, frequencies close to the circuit's resonance frequency, they really prepare the circuit in a particular state, and that can be transferred into the mechanical oscillator. And likewise, frequencies emerging near the circuit's resonance frequency correspond to the state that the mechanical oscillator had just at an earlier time when the interaction might have been turned on. And the fact that those two frequencies are well separated compared to the line width of the resonance circuit, that's given the importance of this resolved sideband factor that was mentioned early in Michel's lecture. And the kind of structures we work with operate far in that resolved sideband limit. So these are really very well separated frequencies. We can think of them as sort of independent fields. A preparation field and an interaction field. So in our first experiments, when we sort of go and take this notion of creating an interaction, take that for a test drive, what we'll do is just rediscover measurement. At a time, we'll say, called t equals 0, we'll suddenly turn on the interaction between the mechanical motion and the electrical circuit. And we'll just look at the microwave fields that leak out of the circuit at its resonance frequency. And when we do that, those microwave fields that emerge, we see a decaying and oscillatory function of time. There's a very clear, you can pick it out with your eye, amplitude and phase of those oscillations. The decay rate is just the rate at which we're extracting energy from the mechanical oscillator as a quantity we know and control. In addition, the oscillation, the frequency of these oscillations is controlled entirely by frequencies we fix in the problem and the Hamiltonian of the mechanical oscillator. And so we know the frequency of these oscillations, we know this decay rate. So rather than just looking with our eyes at the amplitude and phase, we can optimally extract the two numbers we care about, kind of projecting this data into a subspace where the only two numbers that we're going to extract from these many samples in time are the amplitude and the phase. And the amplitude and phase that we extract should be the amplitude and phase that the mechanical oscillator had just before we turned on the interaction. In that sense, it's a kind of pulsed measurement. Now, we could describe the state in terms of amplitude and phase. We prefer to work with a different set of variables. If the amplitude I think of as the length of this little stick and the phase is the angle it makes with some axis, then the variables we'll work with, the so-called quadrature amplitudes, are just the orthogonal axes in that graph, x1 and x2. And we'll extract two such numbers from any measurement of this type. And we'll normalize them in such a way that their squared sum will be equal to the number of excitations in the mechanical oscillator plus some sort of noise quanta which might be present in the problem. So I can show you what will happen if we first prepare the mechanical oscillator near its motional ground state by first turning on the interaction where we've prepared the circuit in its ground state. That is to say, we've done nothing. We've just left vacuum of electromagnetism incident on the circuit. We swap that into the mechanical oscillator, wait for some period of time with the interaction off, and then suddenly turn the interaction back on, by which we measure the state of the mechanical oscillator. And each measurement gives us 1 point in this quadrature phase space. From 400 such measurements, we get a kind of ensemble picture of the state of the mechanical oscillator. We can reconstruct its state, and in this case, it's in a kind of low amplitude thermal state. It's a two-dimensional Gaussian function whose variance is rather smaller than it would be if it were in equilibrium with the environment. And that's if we wait sort of for 100 microseconds. If we wait longer, and that is to say we make these 400 measurements with a longer time delay, we can watch as the phase space of the system evolves from a dense low entropy state into one that occupies a much larger volume in phase space corresponding to a thermal state in equilibrium with a 25 millikelvin environment. In fact, we can take each shot in this movie and just find the average energy associated with that expressed as number of phonons and plot that as a function of the time delay and watch as the system evolves from close to a coherent state, watch as the mechanical oscillator evolves from near a coherent state to an equilibrium thermal state as a function of time. Now, if the mechanical oscillator is a memory, this is a memory that remembers the number 0. Maybe there are more interesting memories. So let's see if we can teach our mechanical oscillator to remember something more interesting. What we'll do is excite the resonance circuit at its resonance frequency with a coherent microwave field with a particular frequency, a particular phase, a particular amplitude. We will then transfer that into the state of the mechanical oscillator, where we presume the mechanical oscillator is then quivering away, remembering the amplitude and phase of this initial excitation for some period of time. We then turn the interaction off, wait for some time, and then energize the measurement. And when we do that, we again get this dense cluster of points, 400 such measurements, which characterize the statistics of the state of that mechanical oscillator. But now it's displaced in phase space by the amplitude and phase of that initial microwave signal. And I can illustrate that in the following way. Let's imagine that I, say, used one of 4 different coherent microwave fields to begin with, which I can color code with one of 4 different colors, and then color the measured values with the color used in the initial microwave field. And when we do that, we can see indeed that we recover the amplitude and phase of the field we cared to remember. And that's if we wait for about 200 microseconds, a relatively long period of time compared to the coherence time of, say, the small integrable superconducting qubits. Of course, I have to make that caveat now that the so-called 3D cavity qubits exist with their very long coherence times. But if we wait 20 milliseconds, we can see that we return back to a thermal state where the distribution in phase space is now much larger than it is when we prepare in a coherent state. And so let me just emphasize, I'll get to just a second, Danielle, halfway into the sentence, I really want to finish this one. Let me just emphasize the following point. It's yes, for a mechanical oscillator, one could always exert some force in an oscillatory way and create a displacement in phase space. But if you started in a thermal state, you would end up in a displaced thermal state. You would not cool the mechanical oscillator. You would not prepare it in a pure quantum state. Here with this sort of transfer protocol, what we're doing is exchanging the pure coherent state of the microwave field for the state of the mechanical oscillator, simultaneously displacing it in phase space and getting rid of a lot of entropy. Go ahead, Danielle.
Can you characterize the fidelity of the retrieval?
It is possible to characterize the fidelity of the retrieval so long as I limit myself to Gaussian states. And I'm not ready to say what the number is yet. It's in the vicinity of 50%. So in particular, keen-eyed as you are, you'll have noted that the coherent amplitude here is relatively larger than 1 quanta. In order to characterize the fidelity, we've looked at the average behavior when the displacements are more like 1 phonon's worth of energy.
And what is the average number of photons in the electromagnetic mode for these alpha coherence?
Good question. So it's the beauty of a beam splitter interaction is we can be very sloppy with the coherent state here, transferring, say, only 20% of it into the mechanical oscillator. And of course, one still ends up in a coherent state in the mechanical oscillator, just smaller than it would have been. And so that's roughly the right number. We sort of, a fifth is transferred, not for any particular reason, simply, well, there are 2 important points to make. One is that the transmission line slides by the resonance circuit, which means that the mode that we couple to naturally is a superposition of 2 waves that propagate from left and right, but we only inject a coherent state from the left. So we lose half of the energy that way. And the other half comes because, well, the other fraction really comes because we don't tailor the pulse the transfer, it's just a square top. Whereas this field also has kind of a square top. It's constant power on and then turned off. And the overlap then is only something like 20%. Again, the sloppiness that we get away with because we're working with coherent states. I can illustrate the distinction between energy and entropy in this problem in the following way. If I plot the average number of quanta in between these shots as a function of time delay, the energy is independent of how long we wait. Even though we've prepared the mechanical oscillator close to a pure quantum state, and then it's going to thermalize eventually with a higher entropy thermal state, the energy is independent of the time delay. And that's because I've rigged the problem. I've chosen a coherent amplitude such that there are as many quanta of energy in the coherent field as there will end up being in the thermal state. And if I decompose this energy into two pieces, one associated with the displacement of the coherent field from the origin in phase space, I can watch that piece decay exponentially in time as the system forgets the coherence that we'd like it to remember. And at the same time, we can watch the entropy leak back in. And even though the energy is constant, of course, the entropy is not. The volume in phase space is expanding. Okay. So I think I started this talk telling you some story about using a mechanical oscillator to create a synthetic interaction between two otherwise non-interacting systems. I'll give you a concrete example of that and something that we're very excited about right now. We endeavor to create an interaction, a quantum coherent interaction between electricity and light, that is to say between microwave and optical fields, where it's the joint interaction of microwave fields and light fields with a single mechanical oscillator that will create that coherent interaction. And we're motivated by the following fact. Let's see. Oh, I think maybe I'll skip this section. Yeah, very good. Here's where I want to start. We'd like to create an interface between light and electricity that uses the mechanical oscillator as an intermediary. And in this work, I collaborate with Cindy Regal and Ray Simmons, who have research groups in Boulder as well. We're motivated by the following fact. Following the kind of amazing work that came out of Santa Barbara, Max Hofein's working with John Martinez and Andrew Cleland really demonstrated that there's an extraordinary ability to create arbitrary quantum states of microwave fields, to simply write down any arbitrary quantum state of a harmonic oscillator and then prepare that state as a state of a microwave resonance circuit via its interaction with a superconducting qubit. The pictures here are sort of an illustration of that arbitrary quantum control. And states of this type play a role in things like quantum communication. Regrettably, if one wanted to communicate with states of this type, you would need to be connected to the other party via a 10 millikelvin phone line. And that's a profoundly impractical thing. On the other hand, in optics, there's the ability to communicate over long distances and also store information for long periods of time, but not quite the same ability to really create and manipulate arbitrary quantum states. And so it would be nice to have an interface which would allow you to make use of this arbitrary state control at microwave frequencies and then convert that to a light field. And so we imagine, in a way, in our kind of highly schematic picture, that some interesting looking arbitrary quantum state living inside of its 10 millikelvin environment could be imposed on a laser light field and removed from the cryostat. And so again, we imagine creating a synthetic interaction between an electrical circuit and an optical field using a mechanical oscillator. Again, now that we can really beat the interaction of the mechanical oscillator with the environment, it's possible to imagine a kind of bus like this, a sort of conduit for quantum information that would pass through the mechanical oscillator. So very schematically, the strategy we're pursuing is to build an inductor-capacitor resonance circuit similar to the type I've shown you, but the mechanically compliant element will be a thin membrane that we metallize in one section, and we leave as a pure dielectric slab in another section. The dielectric piece will live inside of the waist of a Fabry-Perot cavity, and its motion will tune the resonance frequency of that Fabry-Perot cavity, essentially moving the dielectric from regions of high optical intensity to low optical intensity, while its motion simultaneously modulates the resonance frequency of that LC circuit. And I sort of, in my very low-tech animation, indicate that both electrical mode and optical mode are coupled to the same mode of mechanical motion. And then we'll inject microwaves into the circuit and have a light field come out. Okay, not just a light field, but one which knows really is just a map of the quantum state of the microwave field that emerges as a quantum state of the light. And so what is this membrane? Well, we'll use the kind of suspended silicon nitride membranes that one can purchase commercially. They are essentially 50 nanometers thick or thin, but hundreds of microns, even a millimeter in cross-sectional dimension. You can see them with your naked eye. And as you can see in the illustration, we'll use a kind of higher order mode, either a 2-1 or a 2-2 mode of these membranes, where one antinode will be the metallized region that will interact with the electrical circuit. So to build such a thing, we actually build 2 chips. One chip we call the bottom chip, and it contains the pattern that will form most of the microwave circuit. On top of that, we bring the metallized silicon nitride membrane. Both have regions where the substrate itself has been etched away so that light can pass through here. We'll bring these 2 metal regions within about 300 nanometers of each other, put the dielectric region inside of an optical cavity, and then detect the motion both optically and electrically. Here's a picture of our bottom chip now. What you're looking at is just a microscope image of patterned superconducting metal. This is an inductor-capacitor resonance circuit. The inductor you see is this sort of box region here. The capacitor formed by these 2 squares. And when we lay on top of that a metallized upper chip, we will realize an inductor-capacitor resonance circuit of the type I've already described. These holes here, these are the holes through which light will pass. So that's kind of a cartoon of the top chip with its patterned metal silicon nitride membrane. We're going to lay that on top of this portion of the resonance circuit. If I just sort of turn on some transparency, you can see the metal will lie on top of the metal and the dielectric regions over these holes. These are pictures of both the bottom and the top chip. The top chip is now the suspended silicon nitride membrane sits right here with its metal patterning here, and then 3 little posts around that land on these little 3 posts here. Now, when I started this work, I did not believe deep in my heart that we would ever really stick these things together well enough and reliably enough to make it work. If I show you a picture, this is now the top chip literally glued on top of the bottom chip, and we're able to bring those 2 metal surfaces within a few hundred nanometers of each other. This is data measured from that device where we're detecting the motion of that silicon nitride membrane electrically. And one of the beautiful aspects of these silicon nitride membranes is they're very high Q objects. They have a Q of about 15 million at 20 millikelvin. Please note that the data here just represents a kind of ring down measurement. We excite the motion of that dielectric membrane, we stop exciting it, and we watch the energy leave into the environment over a time scale measured in seconds. That's, in my world, a long time. So I'll finish up by showing you that we have an equivalent sort of progress on the optical part of this story. This all takes place in the group of my collaborator, Cindy Regal. She builds Fabry-Perot optical cavities. This is a sort of diagram of the kinds of structures she makes. 2 -S end mirrors, one of these suspended membranes, a piezo control knob, and it all gets stuck together in a single piece of metal to form a kind of monolithic, well, that's not one stone, but it's all kind of rigid and glued together, optical cavity. And this is following what we call the membrane in the middle strategy, which was introduced by Jeff Thompson and Jack Harris's group. It's a picture of the actual structure sitting inside of a 4 Kelvin cryostat. And the recent data from the motion of this membrane detected optically is really quite encouraging. I can show you exactly the same kind of data that I showed you for cooling of electrically detected motion, but now this is cooling the motion of this silicon nitride membrane via exactly the same Hamiltonian, but the frequency in the problem is now the optical frequency in the cavity. That is to say, the electrical excitation is now an optical field. In the same sense, though, the intensity of that light field can be turned up. The area underneath each of these peaks indicating the thermomechanical motion goes down and down. I think it's this cyan-colored curve here, which Cindy says has an average occupancy that she's confident is less than 10 quanta. She can continue to turn up the power and does not boast about occupancies below 10 simply because at these very highest powers you can begin to see some structure in the noise floor. And that corresponds to motion of the end mirrors of that cavity. And I think it's just taming that end mirror motion, which at the moment is preventing sort of a more boastful claim about being able to cool to the ground state using these sort of optical techniques in silicon nitride membranes. Okay, I think that's the sort of progress to date on converting microwave fields to optical fields in a quantum coherent way. We've made the microwave half of that problem work pretty well and the optical half work pretty well. We need to marry the two of them. That means putting light into a dilution refrigerator. The initial motivation I gave you was that I was pleased with myself for the fact that I could put microwaves into a dilution refrigerator and not have to worry about light. Unfortunately, I now really need to commit myself to putting light fields into a dilution refrigerator. But aside from that minor detail, we feel very confident that the rest of this interface between light and electricity works well. So I've shown you that we can really cool these mechanical oscillators to their motional ground state. They behave as a kind of coherent memory. Classically, you would say the memory time might be measured in tens of milliseconds. You could estimate a quantum coherence time of hundreds of microseconds. We've been able to kind of recapitulate the story of electromechanics using these ultra-high Q silicon nitride membranes, which play a crucial role for the optoelectromechanics project that we're pursuing now. Thank you very much.